All right, so let's start the classwork problem solution for the chapter 21 or on electromagnetic induction. Okay, all right. So our first question is this one. Okay, the question number 1. So what we are given here? So we are given that we have a square loop whose length of one side is 5 centimeter. Okay, so this is uh, the length. Okay, and it is an uniform magnetic field whose magnitude is 0.160 Tesla. Okay, so what is the magnetic flux? So we have to calculate the magnetic flux when B is perpendicular to the face of the loop. Okay, so the first one is when B is perpendicular to the face of the loop. So let me draw what it means. Okay, so for example, let's say the magnetic field lines are these. Okay, and the perpendicular loop means this. Okay, so perpendicular loop means something like this. Okay, so that means the direction of the area, okay, we call something like this, and the direction of B are the same. Okay, so that means for the first question, cosine theta is equal to cosine 0 degree, and that is equal to 1. Okay, so we have to calculate the magnetic flux. Okay, so here. Okay, so let's first calculate the first one and then move to the second one. Okay, so A magnetic flux is this, B A cosine theta. So cosine theta here is cosine 0 degree. So it's basically B times A. And here B is what? B is 0.160 Tesla, and A is because it is a square loop, so A is something like this. A is L square, right? So L here is 5 centimeter. That means 5 times 10 to the power minus 2 meter square. Okay, so L square is this 5 times 10 to the power minus 2 meter square. So it gives me something like this, 0.00040 Tesla meter square. Okay, all right. Now the next one is, again we have to calculate the magnetic flux, but when B is at an angle 30 degree to the area of the loop. So that means here theta is 30 degree. Okay, so it's basically similar to the last one, but here you have to put theta equal to 30 degree. Okay, so B is very similar, but here cosine is cosine 30 degree. So again it is 0.160 Tesla, and A is again this. Okay, and the additional thing is cosine 30 degree. So if you plug all these values in your calculator, it should give you something like this, 0.00035 Tesla meter square. Okay, so here, yeah, make sure you do not round it off. Okay, so if you round it off, it is 4, right? It is exactly the same to the number A. So please don't round it off here. Okay, all right. Okay, that is B. And number C tells us what is the magnitude of so what is the magnitude of the average current? So we have to calculate the average current if the resistance is this. So resistance is this, and it is rotated from position B to position A. Okay, so it goes from position B to A. So from 0.00035 Tesla meter square to 0.0040 Tesla meter square. Okay, so you have to basically calculate the current. Okay, now you know that current is equal to what? From Ohm's law, we know current is equal to V over R. Okay, so here you can write it's something like this. Okay, EMF over R. So V is the voltage difference or the potential difference or the EMF, right? So we can write the Ohm's law like this. So we know R, we have to just calculate the EMF. Okay, if we know the EMF, we can calculate the current, right? Now here the EMF is the induced EMF, right? You know that in this chapter, the main thing is to understand the induced EMF, okay? So when we have a change in magnetic flux or magnetic field, okay? Basically change in magnetic flux, then we'll have induced EMF, okay? And if you remember, the definition of induced EMF was something like this: N d phi b, delta phi b delta t, right? Here n is basically one loop, so I don't we don't need to write n, so it is basically delta phi b delta t. Okay, and we are basically interested on the magnitude. Okay, so you don't need to worry about the negative sign. Even if you put the negative sign, I basically want to know what is the magnitude of the current. So here negative sign is not that important. Okay, so I can write the magnitude of the EMF is something like this, or I can write something like this: B final minus B initial, right? Magnetic flux final, that means when it is at 30 degree minus when it is perpendicular, and delta t. Okay, all right, so delta t, okay, I missed that information. So delta t is here, it's given 0.140 second. Okay, so we need delta t, so that is 0.140 second, and final one is this. Okay, 0.0035. Okay, even if you put a negative sign, it doesn't matter actually. Let's put the negative sign. So there will be a negative sign here, and then this test, okay, another 0. Tesla meter square minus 0.00040 Tesla. Good. Okay, so if you solve this, okay, you will get yeah, so 0.00036 volt. Okay, so because you know the unit of EMF is volt, so the induced EMF what we get here is 0.0036 volt. Okay, now if you plug this value here, 0.00036 volt, R is 0.012 omega or ohm, and then if you do this math, you should get something like this: 0.030 amp. So the current here in the loop will be 0.030 amp. Okay, all right, next. So here you see on the right hand side, we are given a diagram, and the cross sign tells us that we have a magnetic field, okay, whose magnitude is this, okay, 0.0600 Tesla, and the direction of this magnetic field is into the screen or into the page in your textbook. Okay, and we have a 100 loop. So here the n, okay, the number of loop is n. So this is basically the this circle, I mean this square loop has 100 turns. Okay, so this is the loop, it has 100 turns. Okay, all right, now it says that initially it is in the magnetic field. So in this part the magnetic field is so here the magnetic field is 0.600 Tesla, and here it is 0 Tesla. Okay, so what happened here is it is quickly pulled from the field at a constant speed to a region where B drops abruptly to 0. So it was initially in the magnetic field, and then it quickly moved to where there is no magnetic field. Okay, so you see that here there was, I mean, by doing this, we basically change the magnetic flux. So because there is change in magnetic flux, there will be some induced EMF. Okay, all right. Now it says that at okay, so at t equal to 0, the right edge of the coil is at the edge of the field. So that means what it's shown here, and it takes this much second for the whole coil to reach the field free region. Okay, so the time it takes to go from the magnetic field to zero magnetic field is 0.100 second. Okay, so we have to calculate. So with this information, we have to calculate the rate of change of the flux. So that means we have to calculate the delta phi, delta t. So here, instead of calculating phi separately, here we have to calculate delta phi, delta t. Okay, that means the rate of change of flux. And then the total EMF and current. So we have to calculate the induced EMF and the current. Okay, and to calculate the current we need the resistance. Okay, so resistance also given here. So the resistance is 100 ohm. Okay, and then energy, we have to calculate the energy and the average force required to bring from the magnetic field region to the zero magnetic field. Okay, so several things we have to calculate. Okay, so let's start. Okay, so let's start A. Okay, so first the rate of change of the magnetic flux, delta phi, delta t. Okay, so we know the time, so delta t we don't need to change, and it is the final, let me call it final or final or and then initial. Okay, so the final means this position when the loop is here, when there is no magnetic field. When there is no magnetic field, you know that there is no magnetic flux, because phi b equal to b times a cosine. Here cosine is 0 degree. Okay, because you see that this is perpendicular. I mean, if I draw the direction for the loop, it will be exactly similar to the magnetic field. So we can write cosine 0 degree. So it is basically BA. Now for the final position, B equal to 0. So we can write just minus phi BI delta T. Right? Now let me calculate first phi BI. BI will be B times A, and A, because it is a square loop, it is just L square, right? So what was B? B was 0.600 Tesla, and L is okay, so L is also given somewhere here. I also missed that information. So here, Okay, 5 centimeters, similar to the last problem. Okay. Okay, so 5 centimeter means 5 times 10 to the power minus 2 meter square. Okay, and cosine 0 degree. So it is basically 0.0015 Tesla meter square. So if you plug this value here in this equation, you get 0.0015 Tesla meter square, and then 0.100 second. Okay, it is basically negative 0.015. Okay, and it will be in volt. Okay, so this volt. So the rate of change of the magnetic flux in this case is this one. Okay, number B. So number B is what is the EMF, induced EMF and the current. So induced EMF will be this N delta phi B delta T. Okay, N is 100 loop, so this is 100, and delta phi B delta T is 0.15 volt. Okay, so then minus cancel out, we have 1.5 volt. The current is from the Ohm's law, okay, or this. So induced EMF is 1.5 volt and R was 100 omega or ohm. Okay, so the current will be 0.15 amp, right? Okay. Number C. Okay, in number C, it asks us to calculate the power. Okay, P equal to VI. So here V is this, I is I. So induced EMF was 1.5 volt and current is this. Okay, so it gives us the power dissipated in the loop is this much watts. Okay, all right, and then it also asks to how much energy. So okay, oh, okay, so it asks us to energy, not the power basically. Okay, so in number C, it asks us to calculate the energy dissipated. So here what we calculate is the power dissipated. Okay, so P is the power and it is easy to calculate. Okay, but once we know the power, then we can calculate easily the energy. How? Now write down the equation of power again, and this is from physics 1, right? Power is the rate of change of the energy. Okay, so delta is the change in energy here. So from the power, I mean, we can easily calculate the energy dissipated. Okay, so if we know the power, if we know the time, okay, then by solving this, we can calculate the energy, okay, by using this equation. Okay, so we just calculated the power is equal to this power is this 0.0225 watts. Okay, and time was 0.100 second. So that means the energy is 0.0225 joule. Okay, so this is the energy dissipated in the coil. Okay, so yeah, don't confuse power and energy. Okay, so I initially thought I have to calculate the power. Okay, because power is most common to calculate in an electric circuit. Okay, so that's why I thought initially it was power, but you know that it asks us to calculate the energy, so we have to multiply the power with time to get the energy. Okay, and the last one is, what is the average force required to bring it from the magnetic field to the zero magnetic field? Okay, so let's see how to calculate that. Okay, now we have to go back to our physics 1 knowledge. Okay, so the the concept we need is the work energy principle. Net work done is equal to change in the kinetic energy. Okay, all right. Okay, now W net, we can write something like this: F external D. Okay, and here cosine 0 degree, right? And that's because the force is, so someone pull this in this direction, and the displacement is also happening in this direction. Okay, so that's why in this case, for the work, in the expression for the work, the theta is 0 degree. Okay, so this is different than that angle in the magnetic flux. Okay, and delta ke is basically delta E, what we calculated in the last problem. Okay, okay, so now cosine 0 degree is 1. Okay, so F external D equal to delta E. So we have to calculate basically F external, and that is equal to delta E over D. Now what is delta E? Delta E is this. And what is D? D is basically 5 times 10 to the power minus 2 meter. Why it is this? Because here you see that the question tells us that it takes this second or the whole for the whole coil to reach the field free region. So let's say this point. Okay, so to bring this point to this point, it takes 0.100 second. Okay, and what is this distance? This distance is 5 centimeter. Okay, so when it is out of the magnetic field, now it looks like this. The coil is something like this here. Okay, now you see that this point and the distance between this point and this point is 5 centimeter. So that's why D here is 5 centimeter. Okay, so when you plug 5 centimeter here, you get the force that is equal to 0.45 Newton. Okay, remember that Newton is the unit for the force. Okay, all right, so the force we need is 0.045 Newton. All right. Okay, so we have a airplane that is traveling at this kilometer per hour. So the first thing we should do, because this is in kilometer per hour, you should convert it into meter per second. Okay, because kilometer per hour is not a standard international unit. So if you plug this value, you get an incorrect result. Okay, so first thing you should do is convert this into meter per second. Okay, and in physics 1, you did it several times, so I'm not going to show it. If you need it, please go back to physics 1 concept and then see that whether you get 1000 kilometer per hour is equal to this. So I got approximately 278 meter per second. So check that. If you cannot get this, let me know. Okay, all right, so velocity is given. Okay, and then what else we are given? We are given the magnetic field, earth magnetic field. Okay, and that is 5 times 10 to the power minus 5 Tesla, and it's perpendicular. Okay, so what it means that the plane is perpendicular to this magnetic field. Okay, so here we are just given the vertical component, so the vertical component is something like this. Okay, yeah, so we are given this because we it will be easy to plug in the calculation. Okay. Now what we asked to calculate is the potential difference or the induced EMF. Okay. So what is the potential difference or induced EMF between the wingtips that are 70 meter apart? Okay. So that means the length of the plane is 70 meter from here to here, it is 70 meter. Okay. So this 70 meter. Okay. Now this is very similar to the motional EMF. Okay, so we get the EMF due to the movement of the conducting wire, something like this. So here you can think that this is a conducting wire. Okay, this plane is a conducting wire. There is no change in the magnetic field. So here we are basically changing the area of the loop, some loop. Okay, so the the equation we derived when we talk about the motional EMF was something like this: E, the induced EMF, equal to L V B or BLV, something like this. Okay, where L is the length of the conducting wire, V is the speed of the conducting wire, and B is the magnetic field that is perpendicular to the loop. Okay, so here everything matches. Okay, so we can just plug the value and calculate the EMF. So L is 70 meter, V is 278 meter per second, and the magnetic field is 5 times 10 to the power minus 5 Tesla. Okay, so altogether it gives me 973 volt. Okay, approximately 1 volt. All right. The next one is very similar. It's again the motional EMF. Okay, so what we are given, okay, the rate of blood flow in our body vessel can be measured using the apparatus shown in this. Okay, so normally if we want to know what is the velocity of our blood in the vein, we use this kind of thing. So you see here we have a magnet. So this is a magnet. This and this is a magnet. You see the north and south pole, and this is the vein. Okay, and then you measure the induced EMF here. Okay, by using this apparatus. Okay, if you just put the some device here and it connected to voltmeter, it's basically, if you place your one probe here and another probe here and you connect it to a voltmeter, it gives you the voltage. Okay, all right, and then by doing some calculation we can determine the velocity. So we are going to determine the velocity or the speed of our blood flow in the vein. Okay, now assuming, so to do that, let's assume that the diameter of the blood vessel is 2 millimeter. Okay, so L is here 2 millimeter. Okay, and the magnetic field that is used is 0.08 Tesla. Okay, and then voltmeter gives you the EMF. Okay, induced EMF, that is 0.10 millivolt. So what is the flow velocity of the blood? Okay, so you have to calculate that. Okay, all right, so let's calculate this. So we can start from this BLV, V equal to BL. Okay, so here you see that everything are given for this equation except V, the velocity. Okay, so we can easily calculate the velocity. So velocity is E, the induced EMF over the magnetic field, and then the length. Okay, so here length is the diameter. Okay, so what is E or the induced EMF? Induced EMF is this millivolt, so we have to convert it into volt. Okay, so this is millivolt or the induced EMF. B is 0.080 Tesla, and then L is 2 millimeter. Millimeter means 10 to the power minus 3 meter. Okay, so if you plug all these values in your calculator, you should get something like this: 0.625 meter per second. Okay, so the speed of the blood is 0.625 meter per second. Okay, all right. Next one is about transformer. Okay, so what we are given, so the charger for a cell phone contains a transformer, as you know now. Okay, reduces 120 volt, okay, AC to 5 volt AC to charge the 3.7 volt battery. Okay, suppose the secondary coil contains 30 turns and the charger supplies 700 milliamp. Okay, calculate the number of turns. Okay, so what we are given, okay, so we are given that the primary voltage is this one, secondary voltage is this one. Okay, so here there are several voltage, so you have to understand that it says that the charger reduces 120 volt AC to 5 volt AC. So primary voltage is 120 volt, secondary voltage is 5 volt here. Okay, and then we are given the secondary turn, NS is 30 and IS is also is 700 milliampere. So we have to calculate several things here. The first one is the number of turns in the primary coil. So we have to calculate NP, current in the primary coil, and the power transformed. Okay, all right. So basically we have to deal with the transformer equation. Okay, so if you remember, the transformer equation was something like this: VS or ES, EP, NS, NP. Okay, so you can, instead of EMF as EMF P, you can write VSBP. Okay, it's basically the same thing. Okay, so here we have to calculate the number of turns, NP. So if I solve it for NP, I get NS and then EP, ES. Okay, so if I solve it for NP, I get this, and NS is 30, primary is 120 volt, secondary is 5 volt. Okay, so if you solve this, okay, you should get the large numbers, 720. So primary coil should have 720 turns. Okay, and it makes sense because in primary coil the voltage was 120 volt, right? More the volt, more the turn; less the volt, less the turn. Okay, so the turn in the primary coil is 720. All right, the current in the primary. Okay, so current in the primary, if you remember, you can use this equation: IP, IS, okay, and then NS and P. So this was the equation. Okay, so if I solve it for IP, I get NS and P, IS. Okay, so NS is 30, NP is 720, IS is 700 milliamp. Okay, so you can convert milli to amp, but yeah, I want to get the result in milliamp. So that's why I'm not converting it. Okay, but you can convert it. Okay, so then it will be okay, so let's convert it actually to make everything the same. Okay, so that amp. Now if you solve this, plugging all those number in your calculator, you should get something like this: 029 amp. Okay, all right. All right, so in the secondary coil, the current was 0.7 amp, or 700 milliamp means 0.7 amp. And here in the primary coil, we have 0.029 amp. Okay, so because the voltage is higher in the primary coil, current should be lower. So this tells us that current is lower. Okay, all right. The last one is the power. Okay, so now power, because we neglect the power dissipated in the coil, we can either use the information from the primary coil or the secondary coil. Both will work. Okay, so P, if you remember, P was equal to IV, right? So you can either use the information from the primary or secondary. Okay, so both will work. Let me just plug the value for primary. Okay, so primary current is 0.029 amp, and the primary voltage is 120 volt AC. So the primary the power is basically 3.48 watts. Okay, all right. Okay, so next one is, again, it looks like a transformer problem. Okay, so let's see. So we have this kilowatt electric power is sent to small town from a power plant 10 kilometer away. Okay, the transmission line have a total resistance. Okay, so R is given, and then initial power is given. Okay, calculate the power loss if the power is transmitted at this and this. Okay, so if I draw the situation, it will be something like this. So let's say here we have the power station. Okay, and then let's say this is long distance 10 kilometer. Okay, and here is a small village, and here we are supplying the power from this power station. Okay, now it says that what is the power loss here in this transmission line, given that the R for this transmission line, the whole transmission line, the resistance for the whole 10 kilometer transmission line is this. Okay, normally the resistance of a transmission line is very small. So you see that for 10 kilometer long transmission line, it is basically, the resistance is basically 0.40 ohm. Okay, it's very small. Okay, so if I want to know what is the power dissipated here, so if you remember in one chapter we learned that the power dissipated in a resistor is equal to this I square times R. Okay, so we know R, we have to calculate I. Okay, so if you know what is I, then we are done. Okay, now how to calculate I? Okay, if I want to calculate I, we can do something like this. So you see that the power is this, the given power is this. So normally we use a transformer here, okay, from the power plant to the power line, and then another transformer here. Okay, so before the transformer, for this transformer, okay, close to the power line, okay, in the primary circuit, in the primary coil, the power is 120 kilowatt. In the secondary circuit, the power is also 120 kilowatt, right? So yeah, don't yeah, so this is the power dissipated. Okay, so this power and this power are two different power. Okay, okay, so here we are talking about the transformer power. Okay, so because the transformer power is 120 kilowatt in the primary coil and the secondary coil is 120 kilowatt, so from this equation we can, from this information and this given voltage, we can calculate the current. Okay, because P equal to IV. Okay, so if we know the power, okay, if you know the voltage, okay, we can calculate I, right? So I will be 120 kilowatt divided by 240 volt. Okay, so kilo means 10 to the power 3, 120 times 10 to the power 3 watts, and 240 volt. So for the first problem, when the voltage is 240 volt, the current in the circuit is 500 amp. Okay, so what it means, this transformer supplies current at this. Okay, the magnitude of the current is this 500 amp. So then if I plug it here, 500 amp square times R, you see that most of the, okay, so if I solve it, okay, and R is 0.4, okay, let's plug it. So if you plug these values and use your calculator, you will see that we get something like this. Or 100 kilowatt. So you see that it is very unuseful. You want to send 120 kilowatt power, but 100 kilowatt hour power is almost losing. We are losing this 100 kilowatt. Okay, so we are just getting 20 kilowatt on the other end. Okay, and so that's why it's not useful. Okay, so sending the power from the power line at this small voltage is not useful. If we send this at this small voltage, most of the power will be lost in the power line. Okay, so that's why we need a step up transformer. Okay, so step up transformer will step up the voltage. You know that when the higher the voltage means lower the current. Okay, so if you do the same thing, you can calculate for B, the current will be very small. Okay, and the current here you will get 5 amp. Okay, so you see that we reduce 500 amp to 5 amp. Okay, so when the voltage is higher, current should be lower in the transformer. So in this case, when we send the voltage at 24,000 volt, the current here will be just 5 amp. Okay, then power dissipated will be I square R, and you see it's a very small. I is 5 amp square and then 0.4, and you see that it's only 10 watts is lost. Okay, so 120 kilowatt is too high. Okay, so 10 watts is not that bad. Okay, so out of 120,000 watts, okay, 10 watts is nothing basically. Okay, so that's why when we supply current, okay, or power from the power line, we have to step up, okay. And of course we cannot handle this large voltage at our household, I mean 24,000 volt at our household. So before it going to our house, we have to step down it again. So we use one transformer here to step up, okay, and to reduce the power loss in the power line. And then on the other side, before it goes to our house, we have to step down, okay. All right, the last problem, calculate the value of the self inductance, okay. So we have to calculate the value of self inductance of a solenoid, given the n equal to this, l equal to this, a equal to this, okay, and the solenoid is air filled, okay. So we already solved this, I mean derived this question, I mean this kind of problem, right? So we already derived for a solenoid the self inductance is equal to this, okay. Now everything is given, okay. So if you plug these values, you get immediately your result. Okay, so here you have to be careful. So here centimeter square, okay. So centimeter square means you have to convert centimeter twice to meter. So that will be 10 to the power minus 2 and 10 to the power minus 2, okay, or 10 to the power minus 4, okay. Make sure you understand this, okay, because here you have centimeter square, you have to convert centimeter 2 times, okay. Many students make a mistake here, okay. So make sure you understand this. And the length of the solenoid is this, okay. So here you convert 1 time. So if you plug all those number correctly in your calculator, you should get something like this. And the unit of the inductance is Henry, okay. So H is for Henry, okay. So that's it for this chapter. And in the next class, I'm going to start geometric optics, okay. All right.